Yep.
Okay, so welcome.
Yeah.
Okay, so we are starting now. I will introduce Ivan. So it's my pleasure to introduce Ivan Nourdin. So he is a professor of stochastic modeling in Department of Mathematics at University of Luxembourg. Before joining University of Luxembourg, he got a couple positions in France, professorial positions, and then he joined group at University of Luxembourg. This is a very strong group, and in my opinion, and I believe that in opinion of many people, they are doing amazing stuff about Steins-Malevin calculus, and I believe one of central areas of Ivan's research is limit theorems and different applications, and he is maintainer of a really well-known site where a lot of results about Malevin and Stein methods are collected, probably all recent results. Sometimes if I like to check these results, I immediately jump to this site and can find a lot of interesting new papers. Also, Ivan has a lot of responsibilities in our research community, and in particular, for example, he is associate editor of Annals of Applied Probability. He is associate editor of Bernoulli and many other journals. So I always, with enjoyment, read his papers and looking for his new research. And I believe today this is a very good example. Topic is really hot between two areas, between probability and modern developments in deep learning. So we are looking for this talk. And Ivan, the floor is yours.
Okay, thank you very much. Thank you very much for the invitation, for the nice introduction. I'm very happy to give a talk in front of you. So I like the old-fashioned way to give talks. So when it is online, it means that I will use my tablet instead of the Blackboard. And this is why I switch off my camera, because the camera is on the tablet. Okay, so I'm going to speak about functional CLTs for deep neural networks. I don't assume you to know anything about deep neural networks, so I will devote most of my talk to explain what it is and what we can do with it and so on. And then in the end of the talk, or in the second part of the talk, I will explain what we did with my collaborators, so Stefano Favaro, Boris Hanin, Domenico Marinucci, and Giovanni Peccati on this problem, where indeed we used some sort of Marinestein method in order to obtain our CLTs. And so I will explain all this. Okay, so let me start. First, let me explain what is a deep neural network. Maybe I should start with what is a neural network, and I should even start with what is a neuron, mathematical neuron. First, I would like to mention that this is a quite old technology. It was introduced by Frank Rosenblatt in the 50s, in the late 50s, by using the perceptron. But of course, at that time, we did not have a lot of data like we have today, so it was more okay, something interesting, but not very used. But today we really have a deep learning revolution because no neural networks outperform all traditional or all the statistical methods. So today deep neural network are everywhere. So we use them for translation, automatic translation, human level object recognition, where it's particularly strong. ChatGPT, as I mentioned already. Also self-driving cars. So it's really a technology that is widely used now, and there is a lot of interesting questions, mathematical questions we can try to work on this topic. And so what is the idea basically of neural networks? So the idea is really to try to mimic what we believe the human brain does. So what the human brain does. at least at the birth of the field, because now, for instance, ChatGPT is using something called transformers, and it is not really connected to what the brain does, but at the very beginning, and it is what I'm going to explain now, we try to mimic what the human brain does. So first, if I explain what is a mathematical neuron, or artificial neuron, so we can we can think of it as so here I draw a circle. Then I have an input, which is a vector of Rn, so x1, x2, up to xn. And then I will weight these inputs, so with weights w1, w2, up to wn. I have also a bias, let's say b. And so, so the neuron is able to compute the sum of xi, wi plus b. So the weights are given, the bias are given, the input is x1 to xn, and so it computes this. But then this is not what it returns. There is an activation function, which is usually called sigma. So sigma is a function from R to R. So it's called activation function, or in our paper, we used the terminology non-linearity function, or there is also a fire function, which is used as a terminology. And then what is the output? It is so sigma of sum of xi, wi plus b. Okay, so let me just give, for instance, some examples of possible sigma functions. So the perceptron I already mentioned, which was the beginning of neural networks, was the function sigma, which is just a Heaviside function. Okay, so it takes 0 if it is negative and 1 if it is positive. And so you see that whatever the input is, you do your calculation, sum of xi, wi plus b, and then it returns 0 or 1, whether the sum of xi, wi reaches the threshold minus b or not. So coefficients are taken this way. So this is, of course, just binary, 0 or 1, but if we want something which is continuous, we are going to use a S-shaped activation function. Like, so you have the hyperbolic tangent or the sigmoid. Okay, so this is something that will have this form here. So this can be 0, 1, or minus 1, 1, and 0 in between, and so on. So you have the sigmoid, for instance, which is popular, which is 1 over 1 plus exponential minus t. And we have also a last example. So there are many examples, but the last favorite examples, which is a ReLU function, so which takes 0 for negative numbers and then x for positive, or t for positive numbers. So this is a ReLU, which is very popular and very much used. So this is just the maximum between t and 0. Okay, so this is for a single neuron, let's say, but of course, with a single neuron, you do basically nothing. So you have to consider what is a neural network. So I already draw something which looks like a neural network. So this is neural network. So here you have an input, which is like in my previous sheet. Here I take an input in dimension 2, so we can see it as a layer number 0. Then we have an output, which is the last layer here, which is going to be layer number 3. And then we have some hidden layers. So here it's hidden layer 1. And here hidden, sorry, what did I do? Okay, hidden layer 2. And so what happens is that you start with the input x1, x2. You have a layer of neurons. So you apply the strategy I explained previously. So you have some outputs for the first hidden layers, and that serve as input for the second layer of neurons, and so on and so forth. And then in the end, you get here a vector of size 3 as an output. Okay, so maybe I should also draw just to say here that the output is just some values that you will get here, and here. Okay, and so you see that there are some parameters in a neural network, so which is called the architecture. So some parameters. So we have the depth, which is usually written L, which is just the number of hidden layers. Okay, so here, in my illustration, L is 2, right? I have 2 hidden layers, and it's enough to speak about a deep neural network. So deep neural network, so the terminology is not completely fixed, I think, but just deep means that there are some hidden layers. So here they are. So we say that this is a deep neural network. Then each layer of neurons has a width. So it's called N1, N2 up to NL. So this is the width. And this is just the hidden layer sizes. So, okay, here again, so if I look at my illustration, we have N1 is 4, so I have 4 neurons on the first layer, N2 is 3, and that's it, because L is 2. And then I have a sigma, which is so my activation function, or non-linearity function, as we call it in our paper, which is a terminology Boris Hanin likes. So we keep it like this. This is well, here I decided to use the same for all the net. In practice, this is really what people are doing. But of course, we could imagine some also neural networks where the sigma is not the same. So at least in general, we take the same sigma in each layer. But for instance, you could take the sigmoid in the first layer and then ReLU in the second layer and so on. But just for simplicity here, it does not change too much. I will assume that I have the same activation function everywhere. Also, neural networks is called fully connected neural network or dense neural network. Because you see that all neurons of each layer connect to all neurons of the next layer, and so of course it does not mean that in reality they connect, because if you take the weight to be 0, then it's like it is not connected. But at least we have when you draw it, you have a fully connected neural network. So it's not the only architecture for there are a few others which are also popular, but here in this talk I will concentrate on this one. But other architecture are the CNN, so convolutional neural network, the RNN, recurrent neural network, LSTM, long short-term memory, and also the very popular now transformers. So which is the architecture which is used for ChatGPT, for instance. And okay, so there are many research activities around this, both in the theoretical point of view, like in this talk, but also in the very applied point of view, where people are trying to understand what to do, how it works, and so on, in an efficient way, of course. Okay, so this is so I hope now you understand what is a neural network. And now question is okay, so it's a nice object, why not? But how does it work in practice? So how can we use such a network to do something we want it to do? So let me just try to think a bit about this. For instance, let me try to tell you something about digit recognition, which is one of the most, so when you learn neural network, deep neural networks, at first, this is usually the example we give you, because this is something which is you can really do yourself without being too much expert in Python or things like this. So you have access to all the material in order to do digit recognition. So what is digit recognition? It means that you have some pictures of something which are digits, and you want the computer to tell you if it is 0 or 1 or 2 and so on or 9. So of course, if you were in the 80s or 90s, you would have tried to do it the old way, so with the lines of code, trying to find a code that you can write in your favorite language to do this. But this is typically the kind of thing where you have no idea on what to do if you wanted to code this, because we have no idea of what we really do when we see that a picture of a 2, and immediately we say, okay, it's a 2, even if it is a bit rotated, or if it is not written exactly the same way, or even if it looks like a bit 8, but we are able immediately to distinguish between a 2 and 8 and other digits. So it's quite normal somehow to try to do like how our brain does, and so neural networks seems to be a good technology for this. Okay, so in order to implement this idea, so we have to follow several steps. So the first one is first we have to have some data, so data acquisition. So it means that we need some data to train the network. So here the data will have this form. So there will be xi, fxi, and I goes from 1 to the number of data that you have. So each xi is a vector, is a 2. My notations are not very good because here x1 and x2 are the entries of the vector, but here xi here is just our vectors of the size of the input, and f of xi is the value taken by the function f that you don't know, you want to discover. Okay, so here, for instance, you have the MNIST data set, which is an open data set, which is just a collection that you can download, collection of 60,000 training images. So it means images of 0s, 1s, up to 9s, of size. So to make it not so big, so size 28 times 28, so which is 784 pixels. So you have a collections of 60,000 vectors of size 784. So those are your xi's. And you have also the value of f of xi. So the collection tells you if for the 60,000 if there are 0s or 1 or 2 and so on. So you have a collections of xi, the collection of f of xi. So this is a digit f of xi corresponding to xi. Okay, and so this is really your data acquisition. And you have also a testing phase in the end. So the MNIST gives you also a set of 10,000 testing images on which you will use in order to test in the end, to test your network to see whether it's efficient or not, and it manages indeed to recognize digits. Okay, then you have a second step, which is a model selection. So model selection, what does it mean? It means that you are going to choose your parameters. So what are your parameters? This is L, the depth, the number of hidden layers. You are going to choose how many hidden layers you would like to have in your network. Then you are going to choose the width or the number of neurons in each layer. so N1 and L, and you are going to choose which activation functions you want. Okay, so this is related to the architecture I gave you previously. And so, for instance, for digit recognition, you can already have good power. Let's say if you choose even L is 1 and N1 is 15 and sigma is reloop. For instance, if you take those parameters, you get already something which is quite quick to train and then quite efficient. Okay, then you have the so now you have chosen something that that looks like this picture with a given L, given N1 and L, a given sigma. Now you must start your network by fixing the weights, the WIs, and the bias, which are the parameters. So you are going to make an initialization, which is important for my talk because it's exactly here that I will start speaking about Gaussian variables. So you have to you have to make an initial choice for the set theta of of weights and bias associated to all the neurons. So each neuron has some weights and a bias, and you have a number of neurons. So for all the neurons, you are making an initial choice. So it's a huge vector, a huge set of things in general. Huge, depending, of course, on the value for L and 1 and L and so on, but in general, it can be very big. And so, of course, a possible choice could be, for instance, my initial choice is to set all the parameters to be 0, or to be 1, or to be something simple. But if you do this, it won't work in practice because you will be trapped in local minima in what I'm going to explain later. So in general, not in general, always what people do is that they start with a random weights and bias. They take at random, and the easiest random way to do it is to take them Gaussian. Okay, so this is really the model that is used in practice. So you initialize your weights and your biases by considering that they are realizations of Gaussian IID Gaussian random variables. Not IID, but independent Gaussian variables. I will tell you about the variance later. Okay, so we have initialization, so which is important in this talk again, because this is exactly here that probability enters into the game. And then we have the optimization procedure. So for this, we need to consider a cost function, which usually is taken to be the function given by this formula. So some for I between 1 and the cardinal of data. Then you compare the output. You got if you start with your entry xi for each I with the set theta, which is the current set, minus what it should be. So of course, with the initial choice, in general, this function L theta is very big. There's no reason why it should be small. But what you would like to do is to make the as smallest as possible, because it's a measure on how close is the output of your neural network with respect to what it should be. So again, theta here is the set, the vector of weights and biases, and so. Then what you do is that you optimize theta with, for instance, gradient descent methods, so which is the usual thing that is done. So there are good processes which allows you to do this quite easily. So by iteration, you will optimize theta, and you will find a value of you will find a set of weights and biases for which the cost is is minimum. And then once you have found something which minimizes L of theta, you test on your testing images, and you see whether the network you constructed is good or not. And so once again, even with L is 1 and N1 is 15, and sigma is ReLU, you can obtain easily and quickly a program that is able to recognize more of 96% of the digits, and quite rapidly. Okay, the problem, of course, with neural networks is that the way it is done and it's trained, it looks like black box, because you don't know what really the computer does when it tells you that this is a 0 or 1 or 2 and so on. In the old way of programming, you have lines of code and you are able to know exactly what was done by your computer. So of course it was really powerful, in the sense that it was able to compute very quickly, more quickly than any human people, but at least you were able to follow what it was doing. But with neural networks, so it's much more efficient for certain problems, like this one, digit recognition. But the drawback is that you have no idea no real idea of why it works so well, and why, for instance, there is no interpretation of the weights and biases. So it's just a collection of numbers, and it turns out that they work well. But okay, so this is why there is a lot of research, of course, around this, to make to understand more how it works, also to understand more what should be the architecture to respond to a given problem, and so on. And so the interest, of course, is to make them in the end more efficient. But already, so we know this well. It works. It works quite well on many things, and okay, it gives rise to like ChatGPT, which is real for me. I use it daily for many things, and wow, it's really impressive the way it works. Okay, so it was my introduction. So we are going to go more on this problem now, but now in this talk, so let me give the context of what I'm going to do in this talk. So this talk, I will fix the number of hidden layers, which can be big or small or whatever, so but fixed. And I will have fixed also sigma, the activation function, with some properties. And I will look at what happens when you make the width of the hidden layers goes to infinity. And I will, as I mentioned already, I will assume that I have a random Gaussian initialization. So, okay, we could try to work with other distributions, but Gaussian here is very important for what I'm going to do. So I will work on this assumption. So let me maybe make a copy and paste of my illustration to add some things and to have it also in this slide. So I have imagine I have this neural net. Okay, so now I'm going to fix a few notations because I will not need them now in the talks. So my input layer, I will call it alpha 0 of x, which is a vector in Rn0. So it corresponds to just to this vector here, x1 or x2. So here n0 is 2, and so n0 in general. So this is the number cardinality of the number of neurons in the input layer. Okay, so I have this, and now let's see the first hidden layer, what we can do. So here to each neuron, I will assume a number. So I is 2, I is 1, I is 2, I is 3, I is 4. So this is the number, the cardinal, the label of each neuron in a given layer. And so now let me see what is alpha 1 of x. So here, this is a vector that will belongs to Rn1, which is so now the cardinality of neuron in hidden layer 1. Okay, so it corresponds to what I get here. This is the first coordinate of alpha 1 of x, second coordinate, third coordinate, fourth coordinate. Okay, so this is this guy here corresponds to this, and this. And so if I want to give a formula for its entry number I, so what is the thing? So for I between I1 and N1, so this is of course first I have sum of for j from 0, so from 1 to N0. And then I have some weights. So weights of 3 parameters, I, j, and 1 here. So 1 to say that this is the layer 1. I to say that I'm looking at the neuron I, and j to say that this is a branch, let's say branch j. So I multiply, so I have this way that I multiply by xj. And then I, using similar notation, I add the bias, and then I take sigma of this. Okay, and so it gives me exactly what is the output of each layer in the hidden layer 1. Okay, and more generally, so I can continue this way. So I have an induction way to do this. So more generally, so I have my alpha 0 of x, which is x in Rn0. Then I will use alpha tilde L of x just to separate the sum of wij, xj plus bi from the evaluation after sigma. So I have I apply the matrix WL to my vector alpha L minus 1 of x. So this guy, so this is a vector in Rnl minus 1. And this guy, it's a matrix, which is an NL times NL minus 1 matrix. Okay, and then I add my bias, so BL, and then it gives me a vector in Rnl. And so finally, when I define alpha L, so without the tilde, it's just sigma of alpha tilde L of x, meaning that I apply entry-wise sigma to each entry of alpha tilde L of x. So it's applied entry-wise. Okay, so this is for, maybe I should have kept some space here. This is how we can get finally the output, which is, so the output is of course alpha tilde of L plus 1. So it's defined by induction. And my initialization, so I say that I will take Gaussian. So Gaussian initialization. Wij, I will consider that this is a Gaussian for fixed I, J, and L, centered Gaussian with variance. I have a parameter CW to say that this is a variance associated to a weight, and I divide by the number, by the size of the layer, just to have something normalized. Each bias BIL is also a Gaussian, so with variance, let's say CB, and all these parameters are independent. Okay, so now I have I have all the parameters which are fixed and given. And so now my quantity of interest is alpha. So my quantity of interest is alpha tilde L plus 1 of X, where X is my input. So I can see this as a field. So X is in Rn0. This guy belongs to Rn L plus 1. And so for each X, which is my input, I have an output, and the way it's computed is fully nonlinear because I have this activation function. And then I would like to understand the behavior of this quantity as N1 up to NL goes to infinity. Okay, so I have a theorem, which is actually quite old. So it started with so the first result on this direction is by Neil in '96. Then there have been some authors which have improved, and the last version, I think the version, the more elaborate version, is due to recently to my co-author Boris Hanin in '23. And so what was proved by Hanin, but following previous studies, was that this guy converged in law precisely in the set of in the space of functions which are R differentiables from Rn0 to Rn plus 1. So I'm not going to tell you what is R here, but it's related. What is R here? It's related to the smoothness of sigma. So it's related to the smoothness or not of the activation function. So if the function is very smooth, you can take R big, and if it is not so smooth like the Relu function, you cannot take R very big. Okay, but of course this is quantifying precisely, and so the limit of this guy is Gaussian. So it takes the form G1 of L plus 1 of X up to Gn L plus 1 L plus 1 of X. So for X in Rn0, so these guys are independent copies and of a Gaussian, one-dimensional Gaussian field, where the covariance is given recursively. So you can compute the covariance first of G1. But it is enough to give the covariance of G1 X, so G1 L plus 1 Y. And you can prove that this is CB, so the parameter I gave you previously, CW, and then expectation, and you can say how it behaves with respect to G1 of L. So we have this formula, which is quite easy. And then, of course, if you want to, you continue by recursion in order to get an expression which does not depend on G1 of which only depends on the big. Okay, so this was what was known, let's say, before we start our study. And so now our work that I did with my collaborators, now it's time to speak about it. It's to associate quantitative CLT. So here it's the CLT, and so we wanted to understand if we can associate speed or rate of convergences in this CLT in the regime, which is the regime usually used by people in practice, where N1, NL indeed goes to infinity, but they are all commensurate with some parameter N. This N goes to infinity. Okay, we have shown many results. It's a quite long paper we wrote, but basically we have results in 3 different families of results. 1D results. So when you have when you N0 is 1, so 1D result. So then D-dimensional results, and then functional results. where you are like in the theorem I just wrote, when you want to associate, keeping track of the process, when you want to compute a rate between the left-hand side and the right-hand side. And so depending on the situation, we get different rates, and as is usual, they are better in dimension 1 because we have many tools and it's easier to do calculations, and we have a lot of nice identities that are no longer valid in dimension D. So in this case, we got that the rate is 1 over n, and I will elaborate this in the rest of my talk. In the D-dimensional setting, we get the n minus 1/2. And so there is room for improvement. So maybe we have to understand if it is n minus 1/2 really, or it's more closer to n minus 1. And in the functional setting, as we might guess, it's always more difficult to work in this setting. So we have n minus 1/8, more or less. Okay, so let me, I would like to focus in the rest of my talk because time is running, so I have to speed up a little bit to the 1D setting, just to explaining what we really did, and to give you some mathematics about this. Okay, so now let me first give you the statement in Stein's methods I'm going to use, or at least to try to use. So the classical, there is a classical fact in Stein's method, which is the Hertz, for instance, of the Marinucci approach, which is the following. So imagine you have a random variable capital F, which is in L2 of omega, so which is square integrable, and also just to make the setting simple to state, let me assume that the expectation has already is already 0, otherwise just subtract the expectation. And then we would like to compare F with its Gaussian counterpart. So we take a Z, which is Gaussian and which has the same variance than F. Okay, so this is the usual thing, and so our goal is to compare the law of F with respect to the laws. And so there are many ways to do it using Stein's method, depending on what is F. But in my setting and in the setting of Marinucci, F is usually regular in the sense that it has a density and so on. So we are in the context where we are going to try to compare the total variation distance between F and Z. And a way to do this, a classical way to do this, is to assume that there exists a random variable V, so that when you compute the classical expectation F phi of F for F, which is C1 and Lipschitz, say, it is not so exactly expectation phi prime of F, but it is expectation of phi prime of F times the weight V. Okay, so we have this. So imagine we have this. So of course, if V would be deterministic and equals to variance of F, you will get that F is Gaussian with variance of F, but in general V is a true random variable. And so in this case, so by applying Stein's lemma in a clever way, so it's classical to get that the total variation distance between F and Z is less than 2 square root of variance of V divided by variance of F. Okay, and what is in general the case is that variance of F is a number, so there is no reason it should be small or whatever, so it's a number. You can think of 1 if you want, if it would be normalized. And so the thing is that this is variance of B, which is small in general, and because to say that variance of V is small is the same as saying that V is close to its expectation, and it's not difficult to see that the expectation of V, if this is satisfied, must be variance of V. So expectation of V is variance of F, and so if the variance of V is small, it means that that V is close to the variance of F, and so f is close to the Gaussian with variance of f. Okay, so this is, for instance, what we used in the Marinucci approach. It was our first thing, because in this case, what I just framed in the context of Marinucci calculus, it is easy to construct such a V and to have a representation that is amenable to analysis. So this is the starting point of what I did with Giovanni. We have a V which is explicit using the operators of Marinucci calculus, and to compute the variance of V, it's something we have a lot of tools to do it exactly, or to have estimation. Okay, so we did a lot of stuff on this, but here it turns out that my F, it's more specific. So I can take advantage of this fact. So just to say, if I just use what is framed, so the classical Stein's method, here I would get n power minus 1/2 even in the 1D. So we realize that in the 1D case, we can go further by changing a bit the usual Stein's method we are using. And so now our context is, let's assume that f in L2 of omega is such that conditionally to W, to V, sorry, conditionally to V, F is a standard, is a Gaussian distribution centered and variance V. Okay, so this implies easily that expectation of F, phi of F, is expectation V phi prime of F, but it's stronger than just assuming this, because of course, if conditionally to V, F is a Gaussian with variance V, then you apply the usual Stein's identity, and you get exactly that expectation F phi of F is expectation V F prime of F. So you go back to the classical thing I was mentioning, but here the fact that you are assuming more actually is that you are really assuming that conditionally to V F is like this, then makes that you can improve and say that the total variation distance between F and Z, this time we can prove that it's less than 8. We don't really care, but what we care is that we get the square of the previous bond. So we get variance of V in the numerator, and so variance of F squared in the denominator. So what is important is that here we have this variance V here to be compared with the square root of variance of V here. And so we can imagine that if we got a 1 over the square root of n in you use the first bound, we'll get a 1 over n using the second bound. Okay, so and here it is exactly what happens. So this conditionally to V and so on when we apply to our problem. Okay, so let me just finish with this. So here, so what is F here? Here F. So I will take that this is alpha tilde L plus 1 of X, and I will take just the first coordinate of the output, for instance. I could take any coordinate of the output. So here L and X are fixed. Okay, and okay, so the one-dimensional is the fact that here I am fixing a coordinate of the output, and just I don't take the whole vector of output. I just either I consider that the output is one single neuron, or I consider that I only concentrate on the first entry of the output. Okay, and now if I compute alpha tilde 1 L plus 1 of X. So that is the first coordinate of W L plus 1 alpha L X plus B L plus 1. So you remember it was, so you don't remember, but I show you. It was, so I am using the end of this slide when I explain how to compute alpha L or alpha tilde L if I know alpha L minus 1. So if I apply here to capital L plus 1, this is what I get. No, I just so this is I just compute the entry explicitly, so it will give me W1J L plus 1 alpha LXJ plus B1 L plus 1. And so I observe that indeed, so the law of F is an N0V, where what is V? So here it's just you have a Gaussianity here and here, which are independent of this guy. So this is conditionally Gaussian, and the V is indeed the CB plus CW divided by NL, and then the norm of alpha L X squared. Okay, so it's obvious. And so if I apply my previous Stein bond, I get that the total variation distance between F and its Gaussian counterpart is less than 8 variance of V divided by variance of F squared. Okay, so now I have to compute or to evaluate the variance of V. Here there is another nice observation. Let me make a small parenthesis, which is that the variance of V, actually, it is 1/3 the force cumulant of F. So let's consider it's true for the moment. I will tell you why in a minute. But then I get that the total variation distance between F and its Gaussian counterpart now is less than 8/3, and the force cumulant of F, so do not rely on V anymore, V being a bit abstract, divided by the variance of F squared. Okay. So we have here you see that this is again a fourth moment theorem, in the sense that if the force cumulant of F is less, and you know how less it is, you expect it to be close to 0 if F is close to the Gaussian, which is what the Neal and Hanin theorem was telling us. So we know already that the force cumulant should be close to 0, but we have to know at which rate. But at least for the moment, we know that if we are able to know at which rate the force cumulant of F goes to 0, we can transform it immediately into a bounce for the total variation distance between F and Z, just by plugging this estimation here. Okay, and so and why do we have this easy thing? The variance of V is 1/3 the force cumulant of F. Why? You can see it just by going back to the definition of what are cumulants. So if I compute the sum of kappa n of F IT power n over factorial n, which is by definition of what is a cumulant, the logarithm of the characteristic function of F. But because F is conditionally Gaussian, the characteristic function of F is nothing but exponential minus t squared V over 2. And now I can also develop this using cumulants of V this time, so sum of kappa m V minus t squared over 2 power m1 over factorial m bigger than 1. And so now I just have to identify it. And for instance, if I look at n is 4, m corresponding to m equals 2, I get exactly that kappa 4 of F is 3 kappa 2 of V, and kappa 2 is the variance. Okay, and so I can now conclude my talk because Hanin, Boris Hanin, in an AAP paper, Analysis of Applied Probability paper, has computed, luckily for us, the asymptotics of all cumulants of F. So he wanted to his CLT, not only to state a CLT, but to say also that to understand how the cumulants go to zero. And if we just take the right statement in this paper, we will obtain that in particular we can focus on the variance. So variance of f is of order of 1. It's normalized. So the normalization is because we assume that by Gaussian initialization, we already put here what we need in order to make it to have a variance equals to 1. Okay, so the variance is not 1, but it's of order 1, and the kappa 4 of f is of order 1 over n. And if we plug this, which is the usual thing, so the fourth cumulant, if you think of f being a sum of independent random variables, because and you know, so by the usual CLT that it's asymptotically Gaussian, then its 4 cumulants will be of order 1 over n. So it's a usual order, it's not a surprising order. So the fact that here we don't get 1 over square root of n, which is the usual order, but 1 over n, comes really from this observation that f is conditionally Gaussian, and this way we can improve by a factor of 2 the rate we have on the total variation distance between f and z. Okay, and I think I will stop here. And I thank you very much for your attention. And of course, I will be happy to answer any question you might have.
Well, thank you, Ivan.
Maybe I put, my camera
Great
again.
talk, great introduction
thank you.
to artificial neural networks. I think that for some probabilists, I think it's a quite interesting topic to learn about. Okay, just unmute yourself and ask questions if you have. I have a small question. So you considered number of neurons in each layer going to infinity. This would be just enough to consider in layer L, for example. So all others, for example, fixed. The last one is going.
Actually here it's really important that all the hidden layers go to infinity. Otherwise, you are not sure to obtain the phenomenon. And the reason why is because here in this theorem, I did not give you the exact formula for the covariance. I just say that it is a recursion. But in order to apply the recursion at each step, you need to have a CLT at each step. And in order to have a CLT at each step, you need all the parameters go to infinity. Otherwise, it does not work the same. And I don't know exactly what would happen in this case.
Okay, yes, thank you.
So it's an interesting question. But,
May I ask another?
Yeah, of course.
Yeah, thanks for the talk. So in this talk, you look only on when weights go to infinity and there is no contribution of optimization. Do you know about the articles or research where they study contribution of optimization in this CLT, let's say? Do you understand what I say?
But I think so you are speaking certainly about this, how does it work in practice, right? So here what I did is only at the initialization stage. I mean, optimization comes after normally. So here we are just trying to understand what happens at the initialization step if you have a number of if the widths of each layer go to infinity in the way I described, and what is what happens in this case, right? Then if you optimize, so this is the next step, but then when you optimize, it's not directly related to the initialization step. So I mean, there are two separated steps. So in what I explained, the optimization plays actually no role at all. I am still in the step 3. I'm just trying to understand steps 3 when step 2, when I make all the parameters of step 2 go to infinity.
And but my question, maybe something
Yeah,
will
please.
change after optimization. Somehow X, Y on this slide here, they also may be random, and they may, I don't know, change somehow the CLT result.
Yeah, of course. But I mean, it's another level of complexity. So if you start with something random and you apply the optimization, which is deterministic, you will get something random in the end. But then, so I'm not aware of any, for the moment, it's an interesting question, but I'm not aware of any study which combine both initialization and optimization procedure. What is
but my
clear
question
is that for the,
did you know about research where they look on initialization and optimization?
Yeah, no, so I'm not aware of such a study. Yeah.
Oh, okay, yeah, thanks.
Also, the set of contributions in this topic is very small. So for the moment, it's quite a new topic. So I mean, everything has to be done. Yeah.
Of course, this is the heart of the difference between neural networks and classical statistics, which always assumes that it's the X's which have the randomness, not the initialization.
Yeah.
Is there some prospect your results with the rates of convergence can be used to explain the phenomenon that with these very large data sets, it seems that neural networks always beat classical methods?
I mean, this is something we observe, so which explain now why all companies are trying, all companies which are something to do with big data and so on, try to use all these techniques, because indeed they outperform all the ways of doing statistics. But yeah, I'm not sure that it has been really understood from a theoretical point of view. So there are still a lot of mysteries around the way it works. For instance, this function L of theta has a lot of local minimums. And when you apply the optimization procedure, because it's a highly non-convex function, so I mean, you are not sure that you reach the global minimum, and in reality, I think you never reach it. And so this is also, for instance, poorly understood why it works efficiently on one hand, but on the other hand, we know that mathematically speaking, there is normally a lot of possible improvement. So I think we are at the very beginning of all these stories. So for the moment, there are a lot of interesting questions, like the one you asked, but there are only a few, from a mathematical perspective, only a few for the moment studies which are really deep and which explain, because there are a lot of papers, but they are observing things, and they are trying to explain why this and this works, but from the mathematical point of view, for the moment, it's quite mysterious. So, yeah.
I have one small question again. So Ivan, you're using central limit theorem, and for central limit theorem, of course, you are using some assumptions like force moment or whatever. Can this assumption somehow guide at least on classes of this function sigma? So you gave some examples of this sigma, which are very important in practice, but practitioners, they use whatever they want, yes? And if you just tell that, for example, if you are using functions of this type, so you can't get central limit theorem, you can't get, for example, okay, everything can explode and so on, can you just go back from your result to the function sigma?
Yeah, well, here I did not give you the right assumption with sigma. Actually, in our results in the functional version, are not only like here when I compare the alpha with its limit, but also we compare the derivative of alpha when we cancel, meaning that sigma is differentiable with the derivative of the limit and so on. But in what I presented, so 1D and so on, we basically can cover any function sigma, starting from Relu to anything, because we don't really need a smoothness of sigma to apply our machinery. So it's quite simple, actually, what I presented here. Once you saw the proof of this more specific Stein's method, you don't really rely on so you need sigma to be Lipschitz, certainly. So just let me try to remind the proof. But apart from this, I think this is also we cannot take the perceptron, the EV side function, but starting from Relu, we have no problem. And no, maybe the question was if we can, using our CLT, can we recover the sigma?
No, not recover, just to tell that, for example, sigma can't explode very quickly or whatever. There are some bounds, because otherwise you will not get proper moments to apply results and convergence.
Okay, yeah. But yeah, we are on the safe side, of course, in the theorem when we ask for Lipschitz properties and so on. Of course, certainly we don't cover all functions sigma, but in practice, really, the one I showed you are the one people are using. So in practice, they are really using sigmoid, hyperbolic tangent, Relu, and try to, yeah. So this is not the most important part of the network, I would say. So more important is the number of hidden layers, number of neurons, number of parameters. Yeah.
Thank you. Other questions or comments, please? So if not, thank you very much. Really very enjoyable and interesting talk, and a lot of, I think, things to think where to apply probability limit theorems and all other stuff. Thank you very much.
Thank you very much.
Thank you. Thank you so much.
Thank you to you. And